Hello everyone, long time no see. I've been a little bit busy, but I'm back trying to make as many videos as I can when I can. So this one's a little bit different. We don't have the paper version. We have the virtual notebook. Gonna bring back the paper one as soon as I possibly can. But I just, still wanted to talk some chemistry with you guys. So hopefully the sound of my voice will have to do for the ASMR aspect of the video. The subject for this evening's ranting is going to be enolates. And I've been studying a lot about enolates recently, and they are extremely useful carbon nucleophiles. So it's often tricky to get carbon to act as a nucleophile. You have to use horrible things like Grignard reagents or lithium compounds like N-butyl lithium. Grignards, they are not very nice to work with, and the yields typically aren't very good. And lithium, N-butyl lithium, is the most stable of its family, but still requires you to be a bit careful because it is pyrophoric, so it catches fire if it comes in contact with air, and you have to be very careful when you're using them in general. So enolates are another way of doing that. They also have a wide range of reactions they can do. And they are formed from ketones, which are very easy to access, or aldehydes. Same thing, really. Not really, but basically, for our purposes, very, very similar. And ketones and aldehydes are abundant, very common. Lots of cheap things contain ketones. Acetone is probably one of the cheapest bulk chemicals out there. And we can also easily manipulate the ketone. After we've used the enolate, we can reduce it back to an alcohol. Or if it's an aldehyde, we can go take it to a carboxylic acid. We can change it to an enamine. We could do lots of things, or an imine. We can do lots of things. So, what actually is an enolate? Well, typically, when something ends in ate in chemistry, we're talking about like a negative charge, a negative ion. So, for example, carboxylate. Okay, that means when the carboxylic acid is deprotonated, you get a carboxylate. So an enolate is like the deprotonated version of an enol. So an enol looks like this. And we have essentially a oxygen, so a hydroxyl group attached to a alkene, a carbon-carbon with a double bond. So enol. So it's a combination of ol for the hydroxyl and the ene of the alkene. And enols normally exist as enols are a tautomer of ketones. So a ketone is kind of in an equilibrium with its enol form, and usually the equilibrium lies very close to the ketone side. So, it's basically always existing as the ketone. There are some exceptions. Phenol is the most famous one. So phenol, you can clearly see that is an enol because it has the double bond next to the OH group. But this is a special case because the resonance keeps it in the ol, the enol form. Because if I were to make a ketone out of this, it would look horrible, like this. Okay, and we've broken the aromaticity, which is a nice stabilizing effect. And so we want to keep that aromaticity, so we keep it as the enol form. But usually we have the ketone being dominant. So we can, however, use acid or base to catalyze the formation of this enol. So we can add acid or base. Normally we add base to get the enol, and we get the enol via the enolate. So if I take my ketone, this alpha proton here, these alpha protons are actually acidic. And the reason why they're acidic is due to resonance forms, which we'll see in a second. But it can be stabilized. So a base can take this proton off and we basically end up with a carbanion. So I've just ripped a proton off of that carbon, which is weird because normally it's very, very difficult to deprotonate just a carbon atom. Normally we think of deprotonation, we don't see carbon CH bonds as acidic. Mostly we see that with O and OO or OH bonds or H's that are part of like an inorganic acid. So we've just taken this proton off, and now we can show a resonance form where this negative charge is passed on through the pi system to the oxygen. So just like how we made our enol on the left here, this is called an enolate. And then this undergoes in equilibrium where it can gain a proton from some proton source to become our enol. But rather than being interested in the enol, we care about the enolate, because this enolate is going to make an excellent nucleophile. If we look at this formal resonance form, that carbon is going to act as a nucleophile, so this alpha carbon here. So rather than acting as an electrophile at our carbon, which ketones normally would, if we add base to deprotonate the enolate, deprotonate and form the enolate, then we can have carbon acting as a nucleophile. And this is going to be really useful. So we take our ketone, we treat with base, and we get an enolate. And we usually form the enolate in situ. Now, the enolate reacts at the carbon atom. Okay, so for example, as a very basic, and this is a simplification of this reaction. Well, we haven't written the conditions, but if I were to add some bromine, I could draw a mechanism that looks like this. And we've now added a bromine onto our alpha position. So the oxygen doesn't react normally. The carbon atom reacts. Now, the problem with enolates is that in terms of making them, you do have to use quite a strong base. So, depending on the enolate that you want to form, we usually use a base that you may have come across called LDA. So this is lithium diisopropyl amine. This base is really useful for lots of different reactions that require a very strong base, but it's also bulky. So the bulkiness means kind of two things. One is that it's not a very good nucleophile because it would bump in the way of, if it tried to react. So mostly LDA will just deprotonate things, which is excellent, because sometimes we don't want our base to act as a nucleophile because it will spoil the reaction. But what it means for enolates is that if you have a ketone and you have ketones that are not symmetric, so there's two different sites for deprotonation. So let's say we've got the contest between these two protons here. If I add base here, which one is going to get deprotonated and which enolate am I going to make? You have two options. You can form the thermodynamic enolate. If you set up an equilibrium by using an alcohol, an alkoxide base like this, and you leave it to equilibrate, then you end up with a thermodynamic enolate. And the reason it's called the thermodynamic enolate is because it's the most stable. So we've got this under thermodynamic control. We leave it for a long time. We let the equilibrium settle. And it settles at the most stable. It settles at the most stable enolate. The reason this is the most stable enolate is because think about the alkene equivalent. So this can tautomerize, not tautomerize, sorry, this can, we can show a resonance structure that looks like that. And hopefully you remember that the more substituted an alkene is, the more stable it is. So this has two R groups, whereas the other enolate would only have, would have none. And so it's the less stable one. Zaitsev's rule, I believe that is. So we can see that the less substituted side is the kinetic enolate. So this is kinetic control, where we basically do it really quickly. And the less sterically hindered enolate forms if we use kinetic control. So we can clearly see that the two R groups are providing steric bulk, so that the base is going to struggle to deprotonate this, compared to this one, which has no steric bulk, really, compared to that. So this is one use of LDA, which is that it's bulky and strong, so it favors this kinetic enolate. So if I have a problem where I need to make the enolate of one, I only want the enolate to react here, then I can use LDA. There are much better ways to do this though. So we'll just briefly talk about trapping enolates. So the best way to get a specific enolate that you want is to trap it. Now, there are a few ways of trapping enolates. The most famous kind of, I suppose, or the most talked about is called a Sylar enol ether, where what you can do is, instead of throwing everything in the same pot and put your base with your ketone and make it react with your substrate, what you can do is make the enol ether first, and you can then trap the particular enolate that you want. Sylar enol ethers, if you use this and your conditions, so let's say we want this to make an enolate of this, and we want the thermodynamic enolate. Okay, so Sylar enol ethers, unless you make it kinetic control, otherwise, you favor, Sylar enol ethers tend to favor the thermodynamic control. So what we can do is treat this with TMSCl and a base, triethylamine. Now, what is TMSCl? Well, TMSCl is trimethyl silyl chloride. And this is just a good way of basically installing a trimethyl silyl group onto a nucleophilic position. And if I treat this with base and my TMSCl, what I'll get is a trimethyl silyl group onto my oxygen. And I've basically trapped the thermodynamic enolate as a silyl enol ether. And when I'm ready to react, so when I'm ready to go through and react to my substrate, what I do is I treat this with methyl lithium. And essentially what happens is, let's rewrite it again. When I treat this with methyl lithium, the TMS group is displaced by the sort of or the TMS group is liberated from the ether to essentially produce tetramethylsilane, and my enolate, which is now represented by this oxygen lithium bond, which we know will basically be a negative charge on the oxygen. So I've now trapped my thermodynamic enolate. If I wanted to trap the kinetic enolate, I could do the same process, but I could use low temperatures and LDA, my strong bulky base, and the low temperatures would mean the equilibrium wouldn't have time to essentially get established, and the first enolate, the easiest enolate that I form, would be, you know, the one that is trapped as the ether. So another way of trapping the kinetic enolate is to use an enamine. So basically, I can react my enolate with a secondary amine like this, with some acid, and what it will produce for me is this. Let me draw that a bit clearer. So this is my kinetic enamine. So you can see that the double bond here is now at the kinetic position. The least substituted enamine has been formed, and this will react like the enolate would. So we'll get that same kind of mechanism where the arrow comes here. The only thing I have to do is to remember to take the enamine off at the end. So after I've done all my reaction, so like I've done whatever I want to do, I now just take it off to reveal the ketone. Okay, so in our next video, if I remember to make it, we will talk about some more interesting things about enolates, and we'll see what interesting things we can do with them. Okay, so I hope you have a great evening. Good night.